Right, let's have a look at making some of these transformation parameters. I've got an example here, and Tambua will be happy. We're using Fiji. I'm talking about the Fiji example that was done a while ago. So, and this comes to some of your work as well, Andrik. The Pacific Islands, so SOPAC, where Andrik's old workplace, requested the help from Geoscience Australia to compute international terrestrial reference frame coordinates at 18 different survey marks on the islands in northern Fiji, from continuous GPS measurements. And this was back in, just for, what did we have? We had about a month, 4 weeks worth of data in 2008. And the reason for this was to support Fiji's claim under the provision of the United Nations Convention on Law of the Sea. This is a very practical reason why countries need to understand the coordinates in their countries, because it affects their maritime boundaries. So they needed some help to transition these coordinates that they had in WGS72. They needed to move them into a realization of ITRF to get them recognized under the Convention on the Law of the Sea. So here are the 18 stations that they had throughout the Northern Islands. And the first step was to observe the GNSS on the survey marks on which they had existing WGS72 coordinates where they had available. So remember, you need the XYZ in the WGS72, and they had that. So they went and then re-observed ITRF to get ITRF coordinates on those same marks. It was done at 18 stations. They got dual frequency observations for 28 days. And the next step is to then compute your ITRF coordinates. In this case, it was ITRF 2005 at the epoch of 2008. So as part of that processing, they included 5 IGS stations from the surrounding area. And remember what we talked about yesterday, those black crosses, the ITRF marks, that's what we've got here as the purple or pink stars. So it's showing you want ITRF information to align with that global datum. You want to be using information from that network from around the area of interest. Because it was available, we also included some information from the Pacific Island Regional Reference Site. So these are now obviously part of APREF, but on some of the Pacific Islands at that time, they also had continuously observing GNSS stations, which are used as part of the Pacific Sea Level and Geodetic Monitoring Project. So they're monitoring the movement of the land and the sea over time. So here's a list on the left-hand side of the data in WGS72. And then on the right-hand side, they've got a list of the coordinates in XYZ from ITRF 2005 at 2008. And the ones in yellow just reflect where we had consistencies across the 2 data sets. So they're the common ones that we had from old and from the new. And then, as I showed you before, we're applying our model, our transformation parameter model, and doing the inversion where the ITRF 2005 coordinates are on the left-hand side and the WG72 coordinates are on the right-hand side. And we're solving for the translations, the scale, and the rotations. So Avit and I were talking about this at lunch. Mathematically, you really only need 3 common points, but the more that you have, the better. The more reliable it will be, the more you can trust it, and the more data you then have to test how well these transformation parameters work in your region. And the transformation parameters are computed, as I said, through a least squares adjustment process, and it's just an inverse of or sort of reversing the way that we do it for the standard least squares adjustment. The translations are computing the mean difference between the corresponding coordinates of datum 1 and datum 2 to get the initial translation values. You've got your scale factor and the rotations between the two different datums. So how it works is you don't really need to understand all the details, because we can provide software that can do this for you. But for those of you who do know least squares, you've got to set up a linearized system, and you're trying to solve for a system of equations. And then it's not a one-off process. You need to iteratively refine the parameters. So you do an initial solve, and then you iterate through, and you keep iterating until you get more and more confidence on the answers. And then very important step at the end is to verify the transformation. So you can use the computer parameters to transform your original coordinates, and then you compare them with the transform coordinates, and you check the differences between them. So there's software like GNSS, CatRef, or other different proprietary software. And just for fun, I also wanted to try this with the assistance of AI. Let's see how this goes. So we've got WG72 on the left, ITRF 2005 on the right. So those of you who have worked with Geoscience Australia will see the results from two very trusted colleagues. That's John Dawson and Gurung Hu, who we've heard about a few times in the last few days. They published a report and gave it through to Fiji that shows what the translations, the scale factor, and the rotations are on the right-hand side. And then, as I said, they did a check. So what were the residuals? Once you transform one data set, transform into the new reference frame, what were the differences between the coordinates? And you can see here that you're looking at around that meter scale for X, Y, and Z. And this is not a reflection on how good the analysis was, but it's more a reflection on how good the input data was. Primarily the WGS72 data. It probably wasn't that accurate, which means you're going to be limited in how good this transformation is going to be. So that's the result we would have expected. And that's also enough for listing maritime boundaries in the law of the sea. It doesn't need to be done at the centimetre level because we're talking about offshore records, right? So metre level, this was good enough for what we needed to do. Now, some people would say, I don't know how to develop transformation parameters. I don't have the software. I can't afford the software. So I wanted to see, can ChatGPT answer this for me? So I asked it to do this for me. I just fed the two data sets. I said, can you transform it? And you'll probably not be surprised to realize the first time I asked, no, it was rubbish results. But then I trained it. I gave it a bit more information. I said, well, what if you remove that station? And what I noticed was that one of the pieces of information in the report was actually giving the wrong data. So it showed me an error. So I fixed that data, I put it back in, and then the next time it was a bit closer, but it was still making some bad assumptions about how to do the mathematics. So after 3 or 4 pieces of training information, I got it to a point where I was matching the residuals that I got from John and Gurung's paper. And at that point, I felt confident that I had the code set up, the software was working, and it understood the data. So it shows how you got to train this AI. You can't just blindly throw it the information. But if you're interested, the software is there, the code's there. The code that worked, this was it. And I said, right, now show it to me as Python code. And then it got me to provide the Python code. So again, I wouldn't blindly go away, use this, but it just shows the good thing about AI and the bad thing about AI. It can be useful and helpful, but it shows how important your professional judgment plays in the development of software like this. So you can use it and it can help you, and you can learn a lot from going through that process as well. You end up learning as you're developing the code, but you don't need to be an expert in Python to have to do it, because it can do that bit for you. You've just got to be able to think your way through the problem. So there's a few points there for discussion in terms of how people do that. And in particular, something that's come up a lot over the last couple of days, how do you deal with these legacy geodetic data? In particular, when you're moving from a reference system or a reference frame in which you don't have an ellipsoidal height or spheroid height. So if you're going from a Clark 1866 datum into a more modern datum, but you have the latitude and longitude in the old system, without the height, you can't then compute the X, Y, and Z coordinates. You can't do that initial conversion, which means you then can't do the transformation. So I might stop there. I'm happy to hear what other people are doing and some issues that they may be having in the development of transformation parameters, and see if we can help you in developing them for your country. Thank you. So, Andrick, this might help you because you were looking for the authoritative ones for Fiji we were talking about yesterday. There they are, Dawson and Hu on the right-hand side. So you should have a quick look now, check if they're the ones that are in epsg.org. See if they're the same or if they're different.
Yeah, I think just to let you know that that report is now published and it's available as well online. So Gurung got that published when we visited Geoscience Australia last year, I think.
Right.
Yeah. So we do have a 2007 report and the 2008 report where we did the South campaign and the North campaign. And that's what we were able to do is work with Geoscience Australia to do the analysis. And I think Simla is what we are looking is the survey team is the Fiji team is will be traveling to Geoscience Australia to build some capacity on the data processing and analysis too. Yeah.
So it from what you just said then, it might be that the southern results are the ones that are in EPSG, but they maybe don't apply or they're different to the ones that are used in the Northern Islands. Maybe there's two different sets of transformation parameters.
Yeah, so what has happened from the first campaign and the second campaign, Gurung has combined the two data sets together and has set at ITRF 2005 and 2008 epoch and have one national transformation parameters now. Right. So we are not yet sure if that is in EPSG now, because that's just recently got published, the report. We will make sure that that goes into the EPSG. So we found issues when we were using surveying software and the GIS softwares where the transformation parameters were different as what we have had established back in 2008. Yeah.
Right. It's very interesting, the Fiji study, Andrew and Nick. It's those RMSs are actually quite within the bounds of the Doppler uncertainty, which is what was used to develop the Fiji datum by, I think, when New Zealand was doing it. Was it New Zealand? New Zealand government did it?
Yes. So New Zealand did that in 1986.
Yeah.
Yeah.
So they would have used Doppler, and
yes.
So that's within the bounds of uncertainty for Doppler. So it's pretty good. Yeah. So the interesting thing is if there's any tectonic deformation between 1986 and 2008, you probably get an improvement if you factor that in as well, but you might not know that. If there's no measurements in between, you can't work that out.
Yeah.
Yeah, and the good thing is with Tambua and Andrick's work, they've got more core stations that are going in. So I think into the future, they'd be looked to try and develop even new transformation parameters, which might come over time as well, which would be good.
Just to let you know, Nick, with these transformation parameters, we have compared with the observed coordinates and converted coordinates and found these residuals all around nationally as well, where we had to observe on an island as well, because there's about like 300 islands in the Fijian archipelago. So that's what we did is basically, did some GNSS observations and seen that against the converted ones too as well. So we found the residuals around a meter or so, or maximum go to 1.5 meter. Yeah.
The other point you raised was about ellipsoid heights. Now, obviously, yeah, an old datum, you might not have ellipsoid heights. They might be just orthometric from whatever technique was used. So we did the PNG transformation from AGD 66 to PNG 94 using the similar approach. But because of we didn't have ellipsoid heights on the old system, we just fed them the same ellipsoid heights as what the GPS had observed. So we basically took that element out of the inversion, simply because we didn't know what the ellipsoid heights were.
How different? So you're saying you use the like the ITRF ellipsoidal height as the ellipsoidal height in the old system. So you're assuming that the ellipsoidal height was the same. Is that what you're saying? Sorry.
Yeah. So perhaps I didn't explain that well. We assumed that those points were ellipsoid heights without any geoid model. So of course, it's a recursive process because, we don't have that information. So we just have to assume that they are, that the Australian national spheroid was the best fit of the Australian Pacific or Australian PNG region, and that the ellipsoid, the N values would be quite minimal because obviously that was the way it was designed to minimize that separation. Right. So we just basically said that they were ellipsoid heights. Perhaps shouldn't.
No, thank you. Thanks for explaining, because some of the things we were talking with our colleagues in Africa about was if you don't have the ellipsoidal height in the old system, in the old frame, something you may be able to do is estimate but you did have an orthometric height or a normal height, you could estimate what you thought the N value was and run it through because it is iterative. And I think what you're suggesting is it worked even without estimating what the N value was, and it still iterated onto a result. Okay. That's good to know. I think that's helpful for some countries, because as you said, that is broadly the assumption that it might have been different in Africa though, because I think they were using what was it called, the war datum or something, War Office datum, and I'm not sure if they used that spheroid was designed to have a minimum N value over their particular country. I think it was something, it might have been a spheroid that was adopted from the UK or somewhere in Europe, which means I don't think you can assume the N values are close to zero, but I can see with the PNG case that you could. So, but what interesting exercise to run through, see if it still resolves. Yeah, thanks. Good. Yeah, he's the guy I would trust. That's good. Thank you.
So what if the residuals is very high, and the suspicion would be on the quality of the ellipsoidal height, because in the old system, we were trying to make the ellipsoidal height 0 instead of throwing them away. I'm not sure is that a good strategy to do that. Yeah, and of course when we do that, the residuals become very good because the height, the third dimension, actually impact the computation.
Sorry. Did you want to answer this, or
just around the height?
Go for it?
Yeah, you're right. You can kind of set the height to 0. We had a little look at the model that underpins the GDA 2020 datum, the plate motion model that's involved there. There's a couple of assumptions with these transformations. The first is that we're looking at rigid body motion. The continent's not kind of deforming when you're deriving the parameters. And the second is that the motion is kind of over the surface of the sphere. Obviously, we live on a kind of an ellipsoidal shaped Earth. So any north-south motion does actually have kind of just in its nature a kind of a change in ellipsoidal height. But even with that 7 centimeters per year north-northeast motion of the Australian continent, the differences were sub-millimeter. So these models are incredibly robust, and I think you can more or less assume that those ellipsoidal heights shouldn't change very much in that third dimension.
What's your? I would also think what's the one you're moving from? If it's from an ITRF to an ITRF, you'd probably be safe. But would that still be the case if you're moving off something that potentially has a geoid ellipsoid separation that's different by 20 meters? Is it still going to iterate in on the final solution? I think if it's small, you can assume it's 0 because you've got iterations. But if it's big, it may be the cause of residuals that you're seeing. Because if you're using a spheroid that's very different position, like the old AGD 66, which it's not geocentric, you may cause problems. But I think in your case in Singapore, you're going from an ITRF to an ITRF. So if it's an old one, I'd try and understand whether or not the geoid ellipsoid separation of that. So was the local spheroid that was developed, was it done to try and fit Singapore well? Then I think you could use what Richard is suggesting. I think would work very well. You could assume that it's 0 or use the ellipsoidal height of the other one. So assume the difference between them is 0. I think that's a fair assumption. That would be worth trying, and then see what residuals you get. And if you're having trouble, the reason could be, one, it could be the heights that is causing more of a problem than we think, or two, the residuals could be that it's not a conformal transformation, and that there's deformation that's happening, and that's causing the bigger residuals. And this is again why it's important to have the more data, the better when it comes to something like this, because then you can figure out, you could take data out from a specific region and say, is it fitting well for that region but not this region? This is when you get into the art form. You can't just throw it all into the equation and assume you'll get the best result. You might need to study each of the individual areas slightly differently.
Now, the quality also will depend on the length of the baseline. Some part of the network, you have a longer baseline. Some part of the network, you have much shorter baseline. Is that also one of the impact? I mean, the distribution of the points, right?
Yeah, I think that the distribution of the points, it might affect the original quality of the uncertainty of the point that you have. But if you're talking about moving from a historical datum on an old spheroid, I think that baseline length is probably going to be the least of your error sources. I think the bigger impact of the error sources is going to come from the uncertainty of the original coordinates, and in particular the height. That's probably where your biggest error source is going to be from. That's what's causing the biggest residuals here. It's nothing to do with your new data set. It's more got to do with the quality of your old data set.
Just want to ask a question regarding the upref, maybe for the Mr. Basara also. There is any plan to develop upref flat motion model? Is there any plan to develop upref flat motion model? Because I think the flat motion model will be give advantage for country to, for example, to replace like CBDF benchmark that are destroyed and they have to replace with the new one. Is there any plan to develop the upref flat motion model?
Thank you for the question. So we still don't have discussion about such kind of a development of such kind of model from the upref solution. And as Nick already explained, that the value of upref is just an providing a time-dependent reference for all contributors, all stations. So I think it is possible to develop an model, deformation model, Barrett motion model from upref solution. But then, so the area covering with upref solution is so wide, and in each area, the source of the deformation and movement is different, and the source is combination of several sources like a plate motion and the internal plate distortion, or an earthquake after slip and a seismic displacement and several sources. So maybe it's difficult to develop a model covering the whole area of upref, and it's better to just develop a model which fit to the feature of each area. Like Japan, Australia, New Zealand, and Indonesia have a very similar feature. So in these areas, maybe the combination of plate motion and plate conversion, and also after slips of the earthquakes, combination could be a way to explain the deformation velocity. But anyway, so maybe we don't have any practical activity and discussion regarding this, and we could discuss this in our working group.
I think that's a great summary of how complicated it is, Basara. Thank you for that. And I'd encourage you to think back to the discussion we had yesterday where we talked about the things that they can be done for you globally and things that are done for you regionally, and then there's things that you need to do nationally. So to take that approach, and how we did it in Australia, for example, is we took the APREF solution, because the APREF solution includes the velocities. So some of the work is being done, but then you have to make a national decision about how do I want to represent those velocities in my country. So in Australia, we chose plate motion model because it was simple. In Indonesia, you might make a different decision about how you adopt that information and how you use those velocities that come out of APREF. You might choose to use a simple model, or you might want to make a more complicated deformation or distortion model. So this is where it becomes a national decision. There's certain things that the APREF community can't do for you because they only deal with the regional component. Those sort of decisions about plate motion models, I think they fall more into the national category where you make a choice and then you do the work. It's not to say that people within APREF can't provide you with assistance, but I think that decision needs to be made at a national scale rather than having someone else develop that kind of model for your country. So thank you. I think that was a great explanation. Yeah, Richard.
Yeah, just to add on to what Basra was saying, it's very hard. I mean, obviously in areas which are in a deformation zone like Japan, New Zealand, there's no real any dominant tectonic plate to use a plate motion model. But that's not to negate the value of a plate motion model in a deforming zone, because that gives you a starting point. So you're looking at residual velocities, which are really due to the the effect of the plate boundary being close by. You're getting an imprint of the neighboring plate motion in the adjoining plate. So those residuals become very useful to analyze. So plate motion model is still a good starting point, which is also, the 14 parameter / 7 parameter, which you can actually strip a lot of those values down to 0 because it's just a rotation. So it's quite useful.